Good afternoon, all of you. So, welcome to the Super 20 series on electronic devices. So, before going to start discussing all the questions on this Super 20 series, let me tell you something. So, yesterday we were doing Maha revision on electronic devices, where we were expected to complete all the chapter like semiconductor physics, p-n junction diode, special diode, MOS capture, MOSFET, and BJT. But suddenly, after 8 hours of the class yesterday, because of the internet failure, class got stopped suddenly. Okay, so because of that, what is the plan for today's? Okay, so today at 2 p.m. now this session I'm going to discuss 20 questions but in the English language. Okay, and in the evening 7 p.m. that is Maha Abhyas in the Hindi channel. Okay, so we will be discussing Maha revision first, the remaining topic that we have left yesterday, and then I will continue the some 20 questions Abhyas today at 7 p.m. Okay, so 7 p.m. we will have first revision, Maha revision, and then we will solve questions, and those questions will be different from this session. Okay, so both will be beneficial for all of you. Okay, so let's start this Super 20 series on electronic devices. So topics that we are going to cover, all the topics: semiconductor physics, p-n junction diode and special diodes, MOS capture and MOSFET, and BJT. Okay, so let's start discussing a very first question. The question is, in a doped semiconductor, EF minus EFI is minus 0.3 electron volt. What is the meaning of this? First of all, let's understand this statement. The Fermi level and EFI is negative. So just in the reverse way, you can write like this, that EFI minus EF is how much? Plus 0.3 electron volt. It means Fermi level is below intrinsic Fermi level. So semiconductor is p-type semiconductor in thermal equilibrium. Okay, that's fine. Where EF is material Fermi level and EFI is intrinsic Fermi level. Okay. At 300 Kelvin temperature, KT/Q is given 0.025 volt. Concentration of electron and holes in the semiconductor is. So we have to find out concentration of electron and concentration of holes. What you have to do is just keep 2-3 pages with you on the table and just try to solve the question with me. Let's see whether you are getting the correct answer or not. Okay, and if you are not able to get the formula for a particular question, then just pause the video. Okay, and continuously it should be go on. Okay. Okay, so let's start this. So EF minus EFI is given negative, so I have taken EFI minus EF is 0.3 electron volt. What is the formula of EFI minus EF? What is the meaning of EFI minus EF? It means it is a p-type semiconductor where Fermi level is below intrinsic, and its formula is KT ln of. So yesterday I told you EFI minus EFP, it is equals to KT ln of P divided by Ni. So from here we can calculate equilibrium holes concentration. EFI minus EFP is given 0.3 electron volt, and this EFI minus EFP is nothing but in the MOS capture we are representing Q phi F, Fermi potential energy Q phi F, that is 0.3 electron volt. Now from here, take this KT in the denominator, take log. If you want to remove log, take exponential, and then P will be equals to how much? P is equals to Ni e to the power of this 0.3, that is EFI minus EFP divided by KT. Okay, so this P holes concentration will be e to the power of this is 0.3. KT is how much? 0.025 volt. So you can write 0.025 volt. Okay, and then this is Ni. Let me solve it by using the calculator. What is this value? So it is e to the power of, we can write it is 0.3 divided by 0.025. Okay, and this value is 162754. Okay, so let me write in a proper format, because here we are having some 1.63, here 1.63 also. So in that manner, it is 1.627 into 10 to the power of how much? 224, and this is 5, and this is Ni. Okay, where you are getting P equals to this much in any option, P is equals to 1.63 roughly. Here we are having P equals to 1.63 10 to the power 5 times of Ni. Here P is 12 Ni, that is wrong. P is here Ni. Here P is 6.4 10 to the power minus 6 Ni. So it is wrong. It is also wrong. It is also wrong. And this is correct. So obviously your option B will be correct. Now you can cross verify by by calculating the electron concentration. How to calculate electron concentration then? Mass action law. N is equals to, you can write Ni square upon P. Ni square upon P means Ni square divided by this. So if you put this in the denominator, Ni will cancel out. So you will be having 10 to the power of minus 5 divided by 1.627 times of Ni. If we calculate this, it is 10 to the power of minus 5 divided by 1.627. Okay. And this is coming to be 6.14 into 10 to the power minus 6 times of Ni. And you can see both P and N, this values, this is P value, this is N value, this is available in option B. 6.14 10 to power minus 6 Ni is the value of N, and P Hole's concentration is 1.63 into 10 to power 5. So it is very simple and straightforward question, we can say, right? Okay. If you are able to solve this question by your own, obviously you are prepared for the GATE examination perfectly, right? Okay, let's move to the next question. The question is, now this question is very rare that a student can solve, okay? Because you are not having the idea about the Debye length, I know very well, okay? The question is, consider a p-type germanium semiconductor at 300 Kelvin with permittivity epsilon of germanium equals to 16 epsilon naught. Doping density Na is equals to 10 to power 14 per centimeter cube. Assume that all the acceptor atoms are ionized and KT/Q is 26 millivolt. Epsilon naught is also given. Debye length is, I know very well, those who have studied electronic devices and studied MOS capacitor in my class, they probably know what is Debye length. So how to calculate Debye length for a p-type semiconductor? The Debye length L Debye is equals to under root permittivity of the material, that is germanium, so permittivity of germanium, epsilon KT, that is small kt, upon Q square into doping. Doping is Na. So epsilon of germanium, okay, ठीक है, into KT upon Q square Na. So one student is asking, sir, ऐसा question exam में आ गए तो क्या करें? In that case, if you don't know the formula, just leave it. If you know, then just solve it, okay? Probably you will be having the questions from your notes only, okay? Okay, so epsilon germanium, that I have solved this kind of expression I have given in the MOS capacitor, okay? You can check in your notes, okay? So epsilon germanium KT upon Q square Na. This small KT/Q you can write. Small KT/U is capital KT, you know very well. So 1Q in the EDC is manageable from the Einstein relationship. So you can write epsilon germanium. 1 small KT/Q, you can write some V thermal voltage. Okay, 1 KT/Q. 1Q will be remaining in the denominator. So you can write like this. Okay. Now epsilon of germanium is given 16 epsilon naught. So it is 16. And epsilon naught is how much? 8.85 10 to power minus 14. 8.85 into 10 to power minus 14 farad per centimeter. Thermal voltage, that is KT/Q, 26 millivolt, that is 0.026 divided by how much? Q is 1.6 into 10 to power minus 19 into Na. Na is the acceptor doping concentration, that is 10 to power 14. Okay, so in this session we will be having some straightforward simple question, and in the evening, okay, we will be having some extraordinary question. Extraordinary means probably every questions you will be solving wrong. Probably out of some 15 or 16 question I will be solving, okay, because of the limitation of the time, because I have to do the Maha revision as well, okay. In that case, probably out of 16 you will be able to solve only 4 or 5 questions only, okay. Okay, so but it is a practice, don't take it on ego, okay. So just solve it, you will be getting the answer definitely. Debye length in the micrometer, then we will convert. So okay, it is under root, this is 16 into 8.85 into 0.026 into 10 to the power of minus 14 divided by 1.6 into 10 to the power of minus 19 into 10 to the power of 14. Okay, so it is 4.7968 into 10 to the power of minus 5 centimeter. Okay, this because this is length, Debye length. Okay, now convert it into the micrometer. Okay, 10 to the power of minus 4 centimeter is micrometer. So it is, we can write 0.479 micrometer. Okay, so now in the question, correct to 2 decimal place we want to write. So it will be 0.48 micrometer. So answer is 0.48. You can write 0.48 as an answer. Okay, 0.48. So this is the answer for Debye length. Okay, so Debye length is the characteristics length up to which the screening effect of the electric field is present. Okay, in any device like MOSFET capacitor or any semiconductor. Okay, now this is the next question, very conceptual question designed by me. All the questions are designed by me. Okay, the question is variation of internal potential in a semiconductor at equilibrium as shown in figure. Variation of internal potential means it is just you know very well, internal electric field is found in the non-uniformly doped semiconductor. When there is a non-uniform concentration of electron holes, we are having internal electric field, we are having internal potential. That internal potential is varying like this. Okay, assume thermal voltage at room temperature is 25 millivolt. Thermal voltage is 25 millivolt. The ratio of holes concentration at point x1, at x1 what is the holes concentration, at point x2 what is the holes concentration, we have to find out the ratio of those holes concentration. Okay, now how to solve this problem? Okay, so let's solve it quickly, very easily. Okay, now let's solve it over here. See, this is your potential diagram. Let me tell you what is the concept that you should keep in the mind. In the energy band diagram, suppose you are having any energy band diagram, valence band, conduction band, intrinsic Fermi level. Simple straightforward thing is, whatever the shape of the conduction band you are having, shape of the conduction band, just notice the replica of that shape will be the plot for electron concentration, and the same plot means electron concentration plot. Electron concentration plot and potential plot are very much identical, very similar. That is the statement. Okay, now in this case what is given? Potential plot is given. If this is the potential plot, then what is the plot of electron concentration? I told you already, the potential plot and electron concentration plot are identical, very similar in the shape. Okay, then you know very well what is the shape of holes concentration, replica of electron concentration plot. So okay, so this is your potential. So on the next page I am drawing, so this is your potential plot. Okay, like this. If this is your potential plot V of x, then what is the plot of electron concentration? Electron concentration plot is nothing but very similar to like this. Just copy paste it like this. If this is electron concentration plot, then what will be the plot for holes concentration? Replica of this. If it is going up, holes concentration will be going down, like this, like this, like this. So this will be your holes concentration plot. Now in the question what is given? Potential is given at 2 points. 2 points means at x1 and x2 it is 100 millivolt, it is 200 millivolt. Okay, so x1, x2, this is 100 millivolt over here. Here it is 200 millivolt. This point is something x2 and this point is something x1. And you have to find out concentration of holes ratio at x1 and x2. Okay, so what is the concentration of holes at x1 and what is the concentration of holes at x2? That ratio we have to find out. Meaning is that, now if you see over here, here you are having some point x1 and here you are having some point x2. So obviously here you can write the holes concentration will be some P1, and here you can write the holes concentration will be something P2. You have to find out ratio of P1 by P2. We have to find out this P1 by P2. Okay, what is the potential difference between this point and this point, my dear friend? The potential difference between these 2 points is nothing but 200 minus 100. 200 millivolt minus 100 millivolt, that is 100 millivolt. And you know very well what is the formula of open circuit potential. That concept you have to use only. Open circuit voltage is nothing but difference between the potential of 2 points. That is equals to KT ln of P1 by P2. On that 2 point, what is the ratio of holes concentration? That is the meaning of open circuit potential, right? What is the ratio of electron concentration? that is KT ln of N1 by N2 is nothing but open circuit potential. So you know very well, here holes concentration is more, here holes concentration is less. Obviously P1 by P2 will be coming greater than 1. That is perfectly okay. Okay, so now what is the difference between the potential? If you calculate the difference between these two potential, like V21 means potential difference between 0.2 and 0.1, that is 200 minus 100, and this is equals to 100 millivolt. This is the potential, and you know very well, if I write potential difference, that is V2 minus V1, that is V21, it will be equals to Vt ln of ratio of holes concentration. Since this V2 minus V1 is positive number, so take Vt ln of some number in the log should be such that this number should also be positive, because left side a positive number, right side should also be positive number. Then you should write P2 by P1 or P1 by P2. P1 is more compared to P2, so write P1 by P2. Okay, this is the case. Okay, so now we have to calculate P1 by P2. So just take V21 by Vt and take log outside, remove the log, anti-log, and then it is P1 by P2. Therefore, P1 by P2 will be how much? E to the power of V21 is 100 millivolt, okay, divided by Vt, thermal voltage given how much? 25 millivolt. So divide by 25 millivolt. These kind of question is very much expected in the GATE examination. GATE is all about these kind of questions only. If this kind of question is coming in the GATE examination, out of 100 students, 10-20% will be able to solve it, and out of 100 students, that is 80 students will be coming out of the examination hall or saying that oh, paper was very difficult. But the thing is that you have not gone through the conceptual understanding of the subject. That is your weakness. 100% I am sure in that case. Okay, so let's solve this. So e to the power of, this is so it is exponential of 100 upon 25 is 4, we can say. So it is 54.598. 54.598. This is the ratio. And now the question is all about correct to 2 decimal places. So 2 decimal places, it will be 54 point. So 2 decimal place, so it will be 0 and this will be 6. So 54.60 you can say. This is the answer, right? Okay, very simple question. Okay, so this is designed by me. Okay, now see, this is the next question. An intrinsic silicon sample has intrinsic carrier concentration of Ni equals to 1 into 10 to power 10 per centimeter cube. Intrinsic carrier concentration is given. Mobility of electron and holes are 1300 and 500 per centimeter square per volt second respectively. Then the required donor impurity concentration. Initially semiconductor is intrinsic. Now we are doing some doping of donor type. Now the statement is, then the required donor impurity concentration that should be added to the sample so that its resistivity drops to 25% of intrinsic value. Obviously, when we do the doping, conductivity increases, resistivity decreases. So the question is, initially it is an intrinsic semiconductor, it is having some resistivity. Now you are doing the donor type of impurity addition. Now obviously resistivity will drop. Now the question statement is, now resistivity is 25% of initial resistivity or intrinsic resistivity we can say. Then the question is, we have to find out how much donor impurity atoms you have added. Assume minority carrier concentration is negligible after adding impurities. When you are doing the doping process, after the calculation, during the calculation, just ignore the minority carrier concentration. That is the question. Okay, so first of all, without doping, initially the semiconductor is intrinsic, and the resistivity of intrinsic semiconductor is 1 upon conductivity. What is the conductivity of intrinsic semiconductor? NiQ_μN plus NiQ_μP. You can write nothing but NQ_μN, PQ_μP. N and P are Ni. Okay, now let's take Ni into Q common. Then in the bracket you are having μN plus μP. Okay, μN plus μP. Okay, so 1 upon NiQ_μN plus μP. Okay, so this is your intrinsic resistivity. Now you are doing the doping. After doping, it will become n-type. So now resistivity will become equals to how much? Resistivity will become equals to NQ-μN plus PQ-μP. But the question statement is just neglect the minority carrier. After doing the doping of donor type impurities, semiconductor become n-type and holes are minority. That's why we can neglect this term. So you can say it is 1 upon NQ-μN. And you know very well, in the n-type semiconductor, electron concentration is approximately Nd. So you can write NdQ-μN. Now the question statement is saying this value is equals to, that is rho of n is 25% of rho of I. And then you have to calculate the value of Nd. This is the question. Okay. So now let's move to the next page. So what we will do is just equate these two term and 25% of rho I. So 1 upon NdQ-μN, 1 upon NdQ-μN is equals to 25% means 0.25 times of intrinsic resistivity. Intrinsic resistivity means Ni into Q bracket μN plus μP. Simple. From here we have to find out the value of Nd. Now now QQ will get cancel out. Both the sides you are having Q. Okay. So now from here Nd is equals to how much? Nd will be equals to how much? This Nd I am taking right side. This is this side I am taking. So this is Ni bracket μN plus μP. Ni μN plus μP this side, divide by, this is 0.25 multiply by μN. Now what you can do is you can write this is Ni upon 0.25, thus divide by μN. So it is 1 plus μP divided by μN. Now put all the values and use the calculator. What is Ni value given in the question? Ni is given 1 into 10 to power 10 per centimeter cube. So Ni is 1 into 10 to the power 10 per centimeter cube, and it is 0.25 multiply by 1 plus μP by μN. What is μP? μP value is given 500 and μN is 1300. Okay. So 500 upon 1300. Now if we solve it, we will be getting the value of Nd. Okay. Obviously. So it is 10 to the power of 10 divided by 0.25 bracket 1 plus 500 divided by 1300. Okay. So it is equals to how much? 5.5384 into 10 to the power 10 per centimeter cube. This is the answer for Nd. 5.5 into 10 to power 10. So 5.53 into 10 to power 10, that is option B. So option B is correct answer for this. Clear? So try to solve along with me only. Okay. This is the best strategy. Sometimes what students think like that, we will get the PDF, then we will try to solve by own. Then in that case, what happens now? Every time you will be accumulating the notes only, and you will not be solving or you will not be doing anything. Even though in the live class it will be time taking, but definitely it will be efficient work, because you will be learning the concept in 3 ways. You are doing your own, you are listening by your ear, and you are also seeing by your eyes to the computer screen or mobile screen. So meaning is that you are having some 3 times more effective work compared to by your own. That's why the class is very much important. Okay. Let's move to the next question. The question is again very simple, straightforward. All the questions will be straightforward. Okay. No complex. Okay. But in the evening, questions will be very much lengthy, but they will be for the abhyas. Abhyas means, okay, abhyas means practicing. Okay. This is just like a exam level question only. All the questions in this session will be exam level. In the evening, whatever abhyas question we will be doing, that will be for the learning purpose only, conceptual learning. Okay. Now question is, in an abrupt P plus N junction, one side is heavily doped, second type is lightly doped, second side is lightly doped. So in an abrupt P plus N junction, the slope of the depletion with W versus under root Vj is given by 8 into 10 to power minus 6 centimeter per under root volt, where Vj is junction potential. Assume silicon permittivity is this much. Doping of the N region is approximately. So what you have to use? Just formula of depletion width. What is the formula of depletion width in abrupt PN junction? W is equals to under root 2 times of epsilon into junction voltage Vj, 2 epsilon Vj by Q into 1 upon Na plus 1 upon Nd. Since it is a P plus N junction, what is the meaning of P plus N? Na is greater than Nd. So if Na is greater than Nd, so here we will be having 1 upon Na plus 1 upon Nd. 1 upon Na will be neglected. So you can write this is 1 upon Nd like this. So this is approximately W. Now the slope of W versus under root Vj. So you can say this is nothing but W, and remaining thing is 2 epsilon upon Q into Nd, and another this is under root Vj. So W versus under root Vj, whatever plot you will be having, the slope of that plot is nothing but this value. So this is the slope of W versus under root Vj plot. So slope 2 epsilon upon Q and D. This slope is given how much? This is given 8 into 10 to power minus 6 by me. Okay. The slope of depletion with versus under root Vj is given 8 into 10 to power minus 6. Units are centimeter, volt, etc. Just take both the sides square. So it is 64 into 10 to power minus 12. Now from here, can you calculate the value of Nd? Yes. So Nd will be how much? Nd will be, take Nd right side, take it in the denominator, 2 into epsilon. How much epsilon value is given in the question? 12 epsilon naught. 12, what is epsilon naught? 8.85 into 10 to the power of minus 14 divided by Q into this number. Q is 1.6 into 10 power minus 19, and this number is 64 into 10 to the power minus 12. Now put all the values in the calculator and get the answer for Nd. So this answer will be, let me use the calculator. So it is 2 into 12 into 8.85 into 10 to the power of minus 14 divided by 1.6 into 10 to the power of minus 19 into 64 into 10 to the power of minus 12. So it is the 2.074 into 10 to the power of 17 per centimeter cube. So 10 to power 17 over here we are having 2.0, roughly 2.0. So 10 to power 17, first of all you have to identify. Okay. So this is the very near answer D, and D is equals to 2.0 into 10 to power 17. Clear? Okay. Okay. Fine. Next question is this. Now it belongs to the PN junction. Again, consider a forward biased P plus N junction. P plus N junction means one-sided junction, where we can consider one-sided PN junction approximation, and diode is ideal. Okay, diode is ideal. So one-sided PN junction approximation means depletion layer will be only one side. Most of the current is because of one type of charge particle. That is the meaning of one-sided PN junction assumption. Okay. Question is, injected current flowing through diode is 1 milliampere. Current means, injected current means in the forward bias PN junction there is an injection current. Current is given at an applied voltage of 2 volt. Okay. Lifetime of minority carrier in neutral N region is 2 microsecond. In the N region, lifetime of minority carrier, meaning is that what is given? Tau P is given, current is given. At room temperature, thermal voltage is this much. Diffusion capacitance of the diode is, what is diffusion capacitance? CD. Yesterday I told you in Maha revision also, CD is tau I upon eta bt. Since it is a P plus N junction, P plus N junction means most of the current is because of holes. So net current I is approximately holes current IP. Okay. And this IP is given how much? 1 milliampere. Okay. So this is given how much? 1 milliampere. And lifetime is given. This is nothing but tau P, lifetime of minority carrier holes. What is CD? Yesterday, tau into I, tau P into IP upon eta bt. Since it is ideal diode, it is indicated. Ideal means eta equals to 1. So just you can write tau P, IP upon thermal voltage Bt. Tau P is how much? 2 microsecond. IP is how much? 1 milliampere. Thermal voltage is how much? 25 millivolt. 10 to power minus 3, 10 to power minus 3 cancel. So it is 2 upon 25 into 10 to the power of minus 6. Okay. And this is CD. and CD unit will be in the, by default, in the farad. Now question is in how much nanofarad it is. So just calculate it. So after calculation, 2 upon 25, I think it will be some 80 nanofarad. So it is 2 upon 25. So 2 upon 25 is 0.08, and this is 10 to the power minus 6. Now you can write it is, so multiply by some 100, then it will be 8 into, this will be 10 to the power minus 8 farad. Now you have to convert in nano, multiply by 10, 80, and then 80 nanofarad. Now you have to write correct to one decimal place. Then what is the answer you will put? So answer by calculator you will put 80.0, just like that. So 80.0 is the answer, 80 nanofarad. Okay, fine. So let's move to the next question. Question is, select the correct statements for electronic devices. What do you mean by this bracket S? It is a MSQ question. So now it is MSQ. Meaning is that multiple options can be correct. The first option is a LED is operated in forward bias mode. Yesterday itself we have seen, yes, LED is operated in forward bias mode. So LED is a forward bias PN junction made up of direct band gap semiconductor. So A is the correct statement. A PN junction solar cell is operated in forward bias mode. Perfectly correct. Okay. No doubt in a solar cell we are not applying any external bias, but internally it is operated in the forward bias mode. Because if you see the IV characteristics, it is showing that voltage is positive. Okay. So across the diode, whatever load we are having in the parallel, that load is having voltage something which is making this diode forward bias. So just say it is a forward bias. Okay. So it is operating in forward bias mode. Second point is also correct. Next, see, a PN junction photodiode. Photodiode is operated in forward bias mode for detection of light. No, your photodiode operates in reverse bias mode for the detection of the photon, that we have seen yesterday as well. C is wrong. Generally, avalanche breakdown mechanism occurs at higher reverse bias voltage compared to Zener breakdown. Obviously correct. You know very well, avalanche breakdown occurs in relatively lightly doped PN junction. Yesterday I have mentioned this point specifically, okay? And avalanche breakdown occurs at a voltage relatively greater than 6 volt. Whereas Zener breakdown mechanism occurs in a heavily doped PN junction at a voltage less than 6 volt. Meaning is that Zener breakdown occurs at lower voltage compared to avalanche breakdown. Or we can say avalanche breakdown occurs at higher reverse bias voltage compared to Zener breakdown. So D is also correct. So what is the answer? We have to identify the correct statement. Always read question carefully. Question statement in the MSQ, after solving the question, identifying the right and wrong statement, just read once again whether they are asking for wrong statement or right statement. Select the correct statement. So correct statement is A, B and D. So answer is A, B, de Villiers. A, B, D. Right? A, B, D. That is the common mistake student do in the examination. Okay, let's see next question. This is the question that I am asking from all of you. Okay, just try to give the answer. Let's see how much dhurandhar you people are. Which of the following equation best describes the charge density profile inside the depletion region of a PN junction diode? Inside the PN junction diode, which one of the following equation can give you correct description of the charge density? Option A is charge density is Q bracket Nd plus P minus Na plus N coulomb per centimeter cube from minus Xp to Xn. Option B is charge density is minus Q into Na coulomb per centimeter cube P side depletion region. And rho B is Q Nd coulomb per centimeter cube N side depletion region. Rho B is minus Q Nd plus P minus Na plus N coulomb per centimeter square coulomb per centimeter cube minus Xp to Xn. Rho B is plus Q into Na minus Q into Nd respectively P side depletion region and N side depletion region. Which one is correct answer? Let's try it. Okay. Okay. So what is the answer? What is the answer? Just try to give this answer. Okay. This is the question that I have framed to to trap you. I am saying now, if I am framing the question in simple questions also, I can trap you. Okay. The trap is those will be giving the option B as correct. They are get trapped in the question. Okay, so B is only correct under depletion approximation. So B is correct under depletion approximation. Depletion approximation. Under depletion approximation, we assume that there is no charge particle inside depletion region. But it is not true, because inside depletion region, you are having ions as well as particle as well, electron and holes. So which one will be the correct? The basic equation of the charge density. What is basic equation of the charge density? Okay, what is basic equation of the charge density? Basic equation of the charge density is, I told you, total positive charge and negative charge you have to club together. What are the constituents in the semiconductor that can give you the positive charge? Sir, donor atoms gives positive charge. How much? Plus Q into Nd. Sir, holes also give positive charge, so Q into P. Negative charge is given by Q into Na, and negative charge is given by Q into N. This equation is valid for all the semiconductor. This is one of the perfect equation. In this equation only you do the modification. In the p side depletion region, you used to say that suppose under depletion approximation, we are assuming that there is no electron, there is no holes, and in the p side there is no Nd. That's why you write minus Q into Na as a charge density on the p side. And the N side depletion region, there is no Na, there is no electron, there is no holes. That's why you write plus Q into Nd on the N side. That's why under approximation, this is the correct answer, under approximation. But nothing is mentioned by me for the approximation. Just you have to go for the exact solution. So this is the answer. So this is the charge density that you can define everywhere. So just take Q common. Then answer is, this is Nd plus P minus this is Na plus N. And I'm saying that if this question is given in the examination, most of the student out of 100, 99 student will mark option B as correct. So which option is correct? Plus Q, Nd plus P minus Na plus N Coulomb per centimeter cube from minus Xp to Xn. So option A is correct. B is wrong, my dear friend. Okay. So B will give you minus 2 by 3. That's why I used to say is never skip. Anyone is not allowed to skip my class. Even though people have got AIR 1 multiple times, 5 times, 6 times, then also in the 7th time, if I am giving the question, they will get trapped in the question, definitely. Okay. Okay, so option A is correct. Let's go to this question. Question is, consider a bar of semiconductor illuminated at one end. Suppose a semiconductor we are having, this is x equals to 0, this is x equals to L, that is 100 micrometer. It is illuminated at x equals to 0, where light energy in is greater than band gap Eg. Okay, so consider a bar of semiconductor illuminated at one end at x equals to 0 with incident optical power of 10 milliwatt. 10 milliwatt incident optical power we are having. Incident photon energy is greater than the band gap energy of the semiconductor. What do you mean by that? That these photons are able to generate the electron hole pair and getting absorbed inside the material. Absorption coefficient of light in this bar at given wavelength is plus 10 to the power 2 centimeter inverse. Alpha is given. Power of the incident photon at x equals to L by 2 is. Very simple question. The concept of this I have given yesterday as well, okay, in the revision. So what is the power at any distance x? Is P naught into e to the power of minus alpha x, where alpha is the absorption coefficient. What is the power at x equals to 0? 10 milliwatt. So that is P naught is given 10 milliwatt into e to the power of alpha is how much? 10 to the power 2 times of x. Now what you have to find out? P of x at x equals to L by 2. What is x equals to L by 2? L is 100 micrometer. So L by 2 is 50 micrometer. But you know very well, here this 10 to power 2 is in the centimeter. Put x also in the centimeter. So just it is 50 into 10 to the power of minus 4 centimeter. So this is 10 milliwatt. This is 10 milliwatt. E to the power of minus this is 100 times of x is how much? 50 into 10 to the power minus 4. 50 into 10 to the power minus 4. So it is how much? Just solve it, okay, by using the calculator. So it is 10 into e to the power of minus 100 multiply by 50 into 10 to the power of minus 4. So it is 6.065 milliwatt. This is the answer. So 6.06. Where is 6.06? Option C. So C is the correct answer. Okay, C is the correct answer. Okay, let's move to the next question. Next question is again very simple. Okay, question is, in a photodiode, incident optical power is 1000 watt. Incident optical power is given. So incident photon power or incident optical power, both are same thing. Okay, so incident optical power or incident photon power, and that is given how much? 1000 watt. 1000 watt is incident optical power. And photon energy is, what is the energy of incident photon? That is 2 into 10 to power minus 8 joules. Okay, if generated photocurrent IL is 2 nanoampere, IL is 2 nanoampere, quantum efficiency of the device is nearest to the integer, correct to nearest integer. What you have to find out? Quantum efficiency. What is quantum efficiency? Yesterday I told you, quantum efficiency is quanta upon quanta, number of electron hole pair generated per second divided by number of photon incident per second. Number of electron hole pair generated per second or number of electron generated per second is IL by Q. And number of photon incident per second is P in by energy of the photon. That is, I used to write like h nu also. P in by h nu. So E in is nothing but h nu, that is photon energy, h nu. Okay. So this is the equation. So you can write. So here h nu is the energy of the photon. P in is the power of the photon. Power upon energy is nothing but number of photon per second. Because you know very well, energy is equals to PT. P into T. Okay, so power upon energy will be equals to how much? 1 upon time T. Okay, so power upon energy is nothing but 1 by T. 1 by T means number of photon incident per second. That is the meaning of this, because power is nothing but total energy of all the photons, we can say. Okay, now so IL is how much, my dear friends? IL is 2 nanoampere, so 2 into 10 power minus 9. Okay, electron charge is 1.6 into 10 power minus 19. We can write this h nu will go in the numerator. H nu is nothing but energy of the photon, that is 2 into 10 power minus 8 joule, divided by this P in is 1000 watt. If we solve it, how much we will be getting? Okay, are you people solving these question or not? Try to solve it. 2 into 10 power minus 9. Don't worry, many of you are attempting some real tests today. That's why some of the students are missing in the live discussion. Okay, they will watch later. Don't worry about it. But you, those who are watching live, just try to solve the question. That is important. So it is 1 by 4, my dear friend. 1 by 4 means it is 0.25. Now in the percentage you have to write. So it is something 25%. So what is the answer? Correct to nearest integer, that is 25. So 25 is the answer, right? 25 is the answer. Okay. Actually what happens now, sometimes students miss some important question and important sessions, okay, because they are not aware of this. Okay, because how student can identify where we will be getting the good questions. So actually these are simple, no doubt. Just go to the back. In this kind of question they get, definitely they get trapped. So they will be missing these kind of good question, conceptual question. Sometimes they are solving very much calculative question, but these questions are very much important, where you get trapped and the questions are looking very simple, like this and like this and like this one. Okay, where this one very conceptual. These are very important for the GATE examination, because nothing new is coming in the exam. Something like this they will give you, and they will be asking to find out the ratio of holes concentration or electron concentration. Student will get stuck definitely, totally blank how to solve this question. Okay, because they are focusing on the formulas, okay, and they are thinking that they have prepared their subject in a very good manner, okay. That is not right for the GATE examination. Okay, so this is done. Okay, now let's move to this question. Now this question belongs to the MOS capacitor. Question is, consider a P substrate MOS capacitor. Now MOS capacitor you are having, it is having P type substrate with flat band voltage VFB equals to minus 0.8 volt. So what is given? Sir, flat band voltage is given. Flat band voltage is given minus 0.8 volt. Oxide thickness TOX is 100 nanometer and permittivity of the oxide is 4 epsilon naught, and epsilon naught is also given. If applied gate to body voltage, the voltage between gate and body is -2, accumulation charge at the surface is in nanocoulomb per centimeter square. We have to find out accumulation charge. What is accumulation? Mode of operation in the MOS capacitor. When the gate voltage, because it is a P substrate, when the gate voltage is less than flat band voltage, you are having the accumulation mode. Ideally, flat band voltage is 0. If you are applying negative voltage, you are getting accumulation. In the P substrate MOS capacitor case, we are talking about. If suppose practically flat band voltage is some X, what do you mean by this? When gate voltage is less than X, it is in the accumulation mode. So accumulation charge means majority charge carrier that are pile up at the surface. So accumulation charge, no doubt in the P substrate, accumulation charge will be holes only, that is positive. So accumulation charge, definitely you can put some mod, because accumulation charge finally should have positive charge, because in the P substrate accumulation charges are holes. But in the case of N-type semiconductor, accumulation charge will be created by electrons, right? So accumulation charge Q is equals to CV. In the accumulation mode of operation, what is the capacitance of the MOS device? COX. Multiply by what is the effective voltage that you are having on the surface. Sir, effective voltage is nothing but how much gate to body voltage is less than the flat band voltage, means difference between these two. If gate to body voltage is equals to flat band voltage, there is no surface charge, flat band condition. If gate to body voltage is different compared to flat band voltage, you will be having accumulation mode. So how much difference between these two voltage we are having? That is nothing but difference between these two voltage. Okay, so COX is your epsilon OX upon TOX, and by default this charge unit is coulomb per centimeter square. Okay, because this is farad per centimeter square. Gate to body voltage, how much is gate to body voltage? -2. What is flat band voltage? -0.8. These two difference between these two we are having. Epsilon OX is how much? 4 epsilon naught. So epsilon naught is 8.85 into 10 to power -14. Oxide thickness TOX, how much? 100 nanometer. 100 nanometer means 100 into 10 to the power of 7 centimeter. Nanometer means 10 to power -9 meter. Meter is equals to 100 centimeter. That's why 10 to power -7. -2 plus 0.8, meaning is that this is 0.8 -2. 0.8 -2 is 1.2 with minus sign, you can say. But there is no meaning of minus sign, because we are calculating the accumulation charge in the P-type semiconductor. That is positive charge finally, because you can take difference like VFB minus VGB. You have to find out difference between these two, okay? So that difference, magnitude of that difference is important, okay, for you. So now finally accumulation charge will be, because you have to find out accumulation charge, and accumulation charge are made up of holes in the P-type semiconductor. So now calculate this value. That's why I have drawn holes over here. Whenever you are revising, you will not get confused, okay? You can click on this notation. 4 into 8.85 into 10 to the power of -14 divided by 100 into 10 to the power of -7 into 1.2. This is 4.248 into 10 to the power of -8 coulomb per centimeter square. Now you have to find out nanocoulomb per centimeter square. Make it 10 to the power -9. So it will be 42.48 nanocoulomb per centimeter square. Okay, so up to 2 decimal place, what is the answer? 42.48 will be the answer. Okay, very simple and straightforward question it is. Okay, let's move to the next problem. Again, a MOS capacitor. Question is, a P substrate MOS capacitor has substrate doping concentration Na value is given, so it is a P substrate MOS capacitor. SiO2 is the dielectric, epsilon of SiO2 is given 3.9 epsilon naught value is given. Given oxide thickness is 20 nanometer as well. Okay, so oxide thickness is given TOX, so you can calculate COX. It means interface trapped charge, or you can say oxide charge, interface trapped charge, oxide charge, okay, oxide trapped charge, 5 into 10 power minus 8 coulomb per centimeter square. So these charges are positive. Assume band gap of silicon substrate Eg is equals to 1.12 electron volt. So band gap of silicon is given 1.12 electron volt. Thermal voltage 25 millivolt. Ni is 1 into 10 power 10. If gate material is N plus polysilicon, now gate material is not metal, it is N plus polysilicon gate material, then flat band voltage of the capacitor is. So we have to find out flat band voltage. Oxide charge is also given. So what is the equation of flat band voltage? First of all, flat band voltage will be work function difference between metal and silicon. That is important for you to calculate. And then it is, if you are my student, then I used to write plus minus QOX upon COX. And that, let me revise it. When oxide charge is positive, this complete term will be having some negative part, that is minus Q upon C, like that. Finally means A minus B. If oxide charge are positive, finally the equation will be like this is suppose some A minus this B number. Meaning is that QOX upon COX will be having some negative. If oxide charge is negative, then this Q upon C will be positive. That is my fundamental. Otherwise, those who are believing in the formula only, they can use this directly, this minus QOX upon COX. So automatically when QOX is positive, overall term will remain negative because of this minus sign. If oxide charge are negative, that one negative sign and this negative sign will become positive. Finally, it will become positive like A plus B. Okay, so both the same meaning. So formula you can by heart like that. Okay, so now your QOX is given. Now you have to calculate COX, and your objective should be calculation of phi m of SI, work function difference. Then your question will be over. Work function difference we have to calculate, but the point is our semiconductor, our metal material is not metal. Now it is a semiconductor. N plus polysilicon. What is the meaning of N plus? By default, whatever doping is given for the gate material, suppose like N plus or P plus, and nothing, no doping is mentioned. By default, what you will consider? N plus means degenerately doped N type. Meaning is that Fermi level is coinciding with the conduction band age. So meaning is that suppose here it is a gate material which is having, this is the conduction band, and here something, a balance band. If this is silicon gate material, substrate is also silicon. So this is, if your conduction band, here will be your conduction band, and here will be your balance band. Very similar. Okay. So this is your conduction band in the oxide. Let me write here, sorry, it is gate material. In place of metal, you are having gate in place, gate material. So gate is N plus polysilicon. N plus polysilicon. Or here you are having P type substrate. Why I'm doing it too much slowly? So that everyone can understand if they are having any problem. This is suppose your intrinsic Fermi level at the center roughly, and it is also intrinsic Fermi level. Okay, this is your intrinsic Fermi level EFI, and this is your balance band. Here also it is conduction band. This is your balance band and intrinsic Fermi level. Since substrate is P type, so obviously your Fermi level will be over here. So this is your Fermi level. Here it is N plus polysilicon. So Fermi level will be coinciding with the conduction band, you can say. So meaning is that this is the Fermi level of N plus polysilicon gate, and this is the Fermi level of this P type substrate. You have to find out work function difference. What is work function? Work function energy from Fermi level to vacuum difference is the work function energy of the gate material. So you can write Q phi G or Q phi M, doesn't matter. So in the case of metal, you can write Q phi M, or in the case of generalized material, you can write Q phi G just. Here, what is the work function of the silicon substrate? Fermi level to vacuum difference, this is Q phi of silicon. This difference you have to calculate, that is work function difference. Meaning is that this minus this we have to find out. Q phi M minus Q phi. This minus this difference is, see, conduction band are in front of each other. So this minus this will be, this total will be obviously this only. So you have to calculate work function difference. Okay, so work function difference will be how much? Work function difference means Q phi G minus Q phi of silicon. Okay, this is called, you can say, Q phi G of Si, or you can say this is Q phi M of Si. Work function difference. This is how much, my dear friend? Just first of all, this is some low value and this is some high value. Some low minus high will be obviously some negative number. Bracket. Now this minus this, if you do, only this portion will be remaining. This you have to find out. Or you can say, if this total minus this we will do, then this will be remaining. So conduction band to Fermi level difference you have to find out. Or we can say from this conduction band to this Fermi level difference you have to find out. Okay. Now how much this distance? Now let me do with another color of the pen. Can you calculate this value? Yes. If you calculate this EFN minus EFI means this value is done. And then can you calculate this value? If you add this plus this will be total this only, that we have to find out. This total value will be this plus this, and this is nothing but this only. And this is nothing but band gap divided by 2Q. Band gap divided by 2, or you can say in electron volt. Okay, so it is band gap divided by 2, this value. So band gap divided by 2. So meaning is that Q phi G minus Q phi of Si is nothing but this minus total this is equals to, you can say, EFN plus minus EFI, that is Eg by 2, plus this value EFI minus EFP, that is nothing but Q phi F. Okay, so this is nothing but Eg by 2 is how much, my dear friend? What is band gap? Band gap is given 1.12. 1.12 divided by 2 is 0.56. And EFI minus EFP is KT ln of Na by Ni. Everything is given in the question. Na is given, Ni is given, KT is given. Let me calculate. 0.56 plus. Now KT is given how much? 25 millivolt. Na is given 4 into 10 power 16 and Ni is given 1 into 10 power 10. Let me put it into the calculator. KT ln of Na by Ni. KT is 25 millivolts, so 0.025. Ln of Na is 4 into 10 power 16 upon Ni is 10 to the power 10. So this EFI minus EFP is 0.3800. So let me write over here 0.3800. Now if we add these two, so it is minus, so 0.56 plus 0.38, and this is nothing but 0.94 minus 0.94. This much is the difference. Okay, minus 0.94 minus 0.94. You can say in the electron volt if you are talking about the energy, or in the voltage form you can write volt. So this is work function difference. So this term is over. Now Qx is given in the question. Cox is epsilon Ox upon Tux. Just put all the values. We will be getting the answer. So flat band voltage will be how much? Work function difference in the voltage format minus oxide charge upon Cox. Work function difference is how much? You are having minus 0.94 minus oxide charge are given how much? Positive oxide charge 5 into 10 power minus 8. 5 into 10 to the power minus 8. Cox is epsilon Ox upon Tox. Let me write Qx. Cox is epsilon Ox upon Tox. That's why Tox will be in the numerator. Epsilon Ox is how much? Epsilon of permittivity of silicon dioxide 3.9 epsilon naught. So it is 3.9. Epsilon naught is 8.85 into 10 to power minus 14. Multiply by Tox. How much is Tox? Tox is given 20 nanometer. 20 nanometer means how many centimeters? It is 20 nano means 10 to power minus 7 centimeter. Now if we solve it by using the calculator, how much this term value we will be getting? So it is 5 into 10 to the power minus 8 divided by 3.9 into 8.85 into 10 to the power of minus 14 into 20 into 10 to the power of minus 7. It is 0.2897. So it is minus 0.94 by minus 0.2897. Okay, so now add these two, 0.94 plus 0.2897. So it is 1.2297, 1.2297. This much of volt is the flat band voltage, right? I think it is so. Just check the calculation, okay? Concept is perfect. If there is any problem or any mistake in the calculation, then avoid it. Don't worry, okay, about that. Okay, do not get stuck in that, okay? So this is very much perfect, okay? So this is minus 0.94, and then this is this, and this is minus 1.2297. Okay, oxide charges are positive, that's why this term will be negative, obviously. 5 into 10 power minus 8 nanocoulomb per centimeter square, sorry, 5 into 10 power minus 8 coulomb per centimeter square, and that is 3.9 epsilon naught is the value of that. So we have put over here, and then 20 nanometer is the oxide thickness. Nano means 10 power minus 7, and then we have solved. Okay. Let's move to next question. This question is this question belongs to MOSFET. A MOSFET operating in saturation region. MOSFET is operating in saturation region. So first of all, this is clear that the mode of operation is given in the question. Drain current is 0.1 milliampere. Has transconductance GM is equals to 1 milliampere per volt. What is the GM in the saturation? Because MOSFET is biased in the saturation, that is given. In the saturation region, transconductance is mu n COX W by L, and you can write VGS minus VT like this. Now question is asking about, okay, or this question is not having VGS minus VT. This is one of the format of the your transconductance. Second format of the transconductance is under root 2 ID mu n COX W by L. This is another format of writing the saturation region transconductance. From here, since ID is given in the question, mu n COX is given, you have to calculate W by L. So from here you can say, if you write GM in the saturation square, then this under root will be gone, and the denominator you can write 2ID mu n COX, then right side we will be having W by L. Meaning is that from here W by L will be is equals to GM square. What is GM? GM is given in the question 1 milliampere. 1 milli means 1 into 10 to power minus 3. Its square, GM square, upon 2 into ID is how much? 0.1 milliampere. 2 ID into mu n COX is 50 micro. Micro means 10 to power minus 6. This will be the answer for W by L. Okay, so just calculate. So obviously it will be 10 to power minus 6. It is 10 to power minus 6. It is cancel out. It is 50 into 200. 100 into 10 to power minus 3. That is 10 to the power of minus 1. And this is 0.1. So it is 1 upon 0.1 into 10 to the power minus 1. 100. So it is 100. So W by L is 100. So W by L is coming equals to 100. So correct to nearest integer, the answer is 100. W by L ratio is 100. Very simple, straightforward question. Nothing is there, right? Okay. In the evening, definitely we will be having some brainstorming questions. Okay. Next question is, this is again good question for you. Let's try. Okay, all of you. The question is, and I will explain you once again also the question. And then I will leave on you how to solve it. Just I will give the time. Consider the N-channel MOSFET as shown in figure. This is your N-channel MOSFET. Let's see how much dhurandhar you people are. With the threshold voltage VT is equals to 1 volt. Threshold voltage of this MOSFET is 1 volt. This is again framed by me. Where applied drain to source voltage VDS changes linearly from drain to source side inside the channel. What is the statement that I have given? If you are applying drain to source voltage, that voltage is changing linearly from drain end to source end of the channel. Obviously, drain side, if you are applying some 5 volt, and then this 5 volt will goes on decreasing linearly, 5, 4, 3, 2, 1, and then 0. Okay. Given VDS, that is drain to source voltage, at y equals to L. What is the meaning of this? This is the length of the channel. This point is origin, your 0, 0. This is your y axis, and this is your x axis. So x equals to 0, y equals to 0 means source end of the channel. Okay. And x equals to 0, y equals to L means drain end of the channel. And what is the meaning of x equals to 0? surface. This is the surface, interface of SiO2 and silicon, right? So the question is saying that the VDS at bi equals to L means at bi equals to L means at the drain end side of the channel, drain to source voltage VDS is equals to 2 volt. And this VDS at bi equals to 0 is 0 volt. Meaning is that from 2 volt to 0 volt, it is changing drain to source voltage 2, 1.5, 1 and like that. If applied gate to source voltage 4 volt, now gate to source voltage we have applied, that is 4 volt, then channel potential at X equals to 0 and bi equals to L by 2 is correct to nearest integer. Find out channel potential at X equals to 0 and bi equals to L by 2. Meaning is that we have to find out potential in the channel at X equals to 0 and bi equals to L by 2. How much is this potential? That is the question. Let's try. If you want to try, everyone. Okay. Meaning is that out of 20 questions, definitely I will be giving some 3, 4, 5 questions new to you. Okay. So that's, you should learn every time some new thing, and it should be very straightforward, definitely. Okay. VC you have to find out at X equals to 0, bi equals to L by 2 inside the channel. So at surface, X equals to 0 means just at the surface, and bi equals to L by 2 means at the center of the channel. What will be the potential? Channel potential you have to find out. Similarly, I can ask you the inversion charge also. From this second part of this question, I can frame, that is find out the inversion charge density at this location. Try it, everyone. Okay, then I will be solving. Don't worry about it, okay? Because you are in the session just to learn only, okay? Some questions you will be solving, and you have to develop the habit that whenever in the examination, if you are not able to click any question in your favorite subject as well, don't get demotivated. There are 65 questions in the exam. But whenever we are doing the learning process, at that time we have to accept all kind of the questions at that time. All kind means conceptual, not unnecessarily formula question, okay? This is conceptual question that can be asked, definitely. Okay, so now what is the solution? You know very well, now I am talking about the channel potential. What is the channel potential? At X equals to 0 and any distance by, this is by horizontal. X equals to 0 means interface of SiO2 and silicon. This is P substrate. X equals to 0 means this line is fixed at here, 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 here. And what is the meaning of this cross point? Bi is changing, okay? So this is your origin. In the downward direction, X is changing, horizontal axis bi is changing. So what is the meaning of X equals to 0? Surface is fixed. At the surface, what is the potential because of the gate voltage? VGS minus VT. If gate voltage is more than VT, the remaining potential that extra than VT we are applying is going to appear at the surface of the channel. So VC at X equals to 0 or at the surface because of the gate voltage is VGS minus VT. And suppose if VDS is also applied, VDS also affects the channel potential, and that potential VDS will be subtracted, and VDS is a function of bi. So channel potential is given by VGS minus VT minus VDS. That's why you know very well, when drain to source voltage is equals to VGS minus VT, MOSFET enter into the saturation, because at the drain end side your channel is not having any inversion charge, any potential. Because this potential is useful for calculating the inversion charge, because inversion charge in the channel at X equals to 0 at any distance by will be equals to, in the inversion region, capacitance is COX multiplied by this VC, X equals to 0 at any distance by. This is the formula for inversion charge. Okay. Now, definitely you have to find out this at bi equals to L by 2. So what is the question asking about? X equals to 0 at any distance by, and bi equals to how much? L by 2. So this is VGS minus VT is fixed at X equals to 0, minus this is VDS at L by 2. What is VDS at L by 2? VDS is varying from 0 at bi equals to 0, and it is varying up to 2 volt. So VDS is how much it is given? VDS at by equals to 0 is how much? By equals to 0. VDS at by equals to 0 is 0. And VDS is given at by equals to L. How much? At by equals to L, VDS is 2 volt. And in the question I have given this VDS is varying linearly with the distance X or distance by. So can you write down the equation of this, who is varying linearly from by equals to 0? It is having 0 value. By equals to L, it is having 2 volt. So what is the equation for VDS? Then you can say by equals to mx plus c. Okay. 2 bracket 1 minus x upon L, you can say something like that. Okay. Or you can say this is slope is 2 minus 0 upon L minus 0. Mx plus c, like that. Na? At by equals to 0, the value should be 0. That's why it is 0. So it is like this. VDS is changing. This VDS is like this. So this VDS is 2 by L into by, like this. So at L by equals to 0, it will be 0. At by equals to L, it will be 2. So this will be the equation that describes the VDS with respect to by. So VDS at by equals to L by 2 is how much? So VDS at by equals to L by 2 will be how much? VDS at by equals to L by 2. If we put by equals to L by 2, L cancel, 2 by 2 is 1 volt. So it is 1 volt. Now put the value of VGS. How much is VGS in the question? VGS is 4 volt. And what is the threshold voltage in the question? Threshold voltage of the MOSFET is 1 volt. So VDS is 4, VT is 1. So it is 4 minus 1 and this is minus 1. This is 2 volt. 2 volt is the answer. So the answer is 2 volt. This is the correct answer. Okay. So this is very important question. Okay. This kind of concept may be asked in the examination. Be careful. Now this is the very simple question. Don't worry about it. Okay. So it is very simple, straightforward. Nothing is new. In the circuit shown in the figure, in the given circuit, switch S1 remains closed. The switch S1 is remain closed and S2 remains open for a long time. For a long time it is open, it is closed. At t equals to 0, switch S1 opens and S2 closes. S1 is open and S2 is closes and remain in this position for long time. Find drain current for t less than 0 and t much greater than 0 respectively. Mu and 𝐶𝐻𝑊 by L is given to you. Okay, let's solve it. So at t less than 0, what is happening in the circuit? Let's do that first and then we will solve for t much greater than 0. So at t less than 0, what is happening? At t less than 0, this switch was closed and this was open. Okay, sir. If this was closed and this was open, so this is open, make it open. And this is closed, so make it close. Okay, so this is just open circuited and this is just closed circuit. So it means this source terminal is connected to ground. Now, can you calculate the drain current? Just first of all, think about whether MOSFET is on or off and in which mode of operation MOSFET is operating. That is important. So right now, what you are having gate to source voltage? Gate to source voltage is 3. It is a N-channel MOSFET, NMOS. VGS is 3. VT is how much? 0.5. So obviously your VGS is greater than VT, so MOSFET is on. Now let's think about whether it is in the linear or saturation. So for that, first calculate overdrive voltage VGS minus VT. VGS is 3, VT is 0.5, so it is 2.5. So this is VGS minus VT. Now what is VDS? Drain to source voltage 2 and this is 0. Drain to source voltage is 2 volt, drain or source voltage 0. Okay, so now this VDS is, my dear friend, is less than VGS minus VT. If it is so, MOSFET will be in the linear. So at t less than 0, MOSFET is in the linear. And in the linear region, what is the current equation in the linear region? Mu n 𝐶𝐿 by L VGS minus VT into drain to source voltage minus half VDS square. So mu and 𝐶𝐻𝑊 by L is how much? 200 micron. So let it written in the same format because the option of all the options are having current in the microampere. Okay. Now what is VGS minus VT? So VGS minus VT is 2.5. Drain to source voltage VDS is 2 minus half times of this 2 square. So it is 200. Just I will write the answer in micro. 2 into 2.5 is 5 minus. This is 4 upon 2, that is 2. 5 minus 2 is 3. 3 into 2 is 600. So 600 microampere is the current for t less than 0. So at t less than 0, current is 600 microampere. So A is having, B is having, C is having, D is 0. So D is not possible. Now let's calculate for t greater than 0. For t greater than 0, specifically you have to find out t much greater than 0 when switch is on the given position for a long time. Okay. So t much greater than 0, what is happening? This switch get opens and this will get closed. Okay, so let's do that. So this is just opened. Let open this and this get closed. So now what will happen? Once this switch is closed, what is the voltage? This voltage 3.5 and this 3.5 is connected at source. So now what is gate to source voltage now? Now gate to source voltage VGS is 3 minus 3.5. This is minus 0.5 and VT is how much? 0.5 volt plus. And it is a N-channel enhancement type MOSFET, my dear friend. Since VGS is less than VT, MOSFET will be off. Cut off. And cut off current is 0 for the MOSFET. So at t less than 0, current is 600 microampere. And for t greater than 0, it is 0. 600 and 0, option A is correct. So A is the answer for this question. Very simple question it is, okay? Nothing new in this question. Let's move to this question. The condition for an N-channel MOSFET to operate in deep triode region. Very simple question I have given to you. Deep triode region. What is the condition for deep triode region? A MOSFET operates in the deep triode region. Specifically, it is N-channel MOSFET. So in the N-channel MOSFET, what is the deep triode region condition? VDS should be much less than 2 times of VGS minus VT. 2 times of overdrive voltage. VDS should be much less than 2 times of VGS minus VT. So VDS much less than 2 times of VGS minus VT. Option B is correct. And this is the condition for deep linear region of operation or deep triode region of operation. Now this question belongs to the BJT. Okay. Question is, which of the following statements is or are true about BJT? For BJT, which of the following statement is or are true? So it is MSQ. In active region, it is used as an amplifier. Yes, BJT act as amplifier in the active region. Everyone knows about it. Next, let's check the option C. Active and cutoff regions together are used as a switch. No. BJT act as a switch in 2 mode operation. Saturation is perfect on switch and cutoff is off switch. So saturation and cutoff together is used for switch application of the BJT. So here it is written active, okay, and this is cutoff. So no, saturation and cutoff are used as a switch, okay. So this is wrong. Let's go to D. Reverse saturation current of collector base junction. Reverse saturation current of collector base junction is CB0, ICB0. Does not change with the temperature. You know very well, when temperature increases, reverse saturation current of collector base junction increases. So it is wrong statement. Let's go to the option B. In saturation region, means saturation mode operation of the BJT, with change in voltage, ammeter current does not change. Question is, in the saturation region, suppose BJT is operating and you are changing the voltage, what do you think? Ammeter current will change or not change? Which voltage first of all? By default, they are talking about the base ammeter junction, input voltage. So if base ammeter voltage, if you are changing, then which of the thing will not change and which are the thing that will change in the saturation mode operation? So in the saturation mode operation, what happens? Collector to ammeter voltage VC become saturate approximately and collector current gets saturate. But in the BJT, even though it is in the active region of saturation mode operation, base current keep on increasing, ammeter current keep on increasing, only collector current gets saturate. Okay, so that is the thing. So that's why this is also wrong. In the saturation region with change in the voltage, ammeter current does not change. Ammeter current change, my dear friend. So let me write this statement on the next page. So in saturation region, what happens? In saturation region of BJT, what happens? Collector current IC gets saturate. But, and this is the basic thing that I used to teach you in the analog circuit. We start from here only. But IB and I keeps on changing. With change in input voltage. And the question statement is saying that even though we are changing the voltage, ammeter current does not change. No, collector current does not change, but ammeter and base current changes. So option A is only correct. So answer is option A. Okay, let's move to the next problem. Next problem is this. Question is, when a germanium PNP transistor is biased at 2 milliampere of collector current. A germanium PNP transistor we are having, okay, and biased at 2 milliampere of collector current. So collector current is given 2 milliampere. It has a base width of 1 micrometer, base thickness WB is 1 micrometer. Okay, the value of diffusion capacitance of the ammeter base junction. You have to find out ammeter base junction capacitance C, or you can say ammeter base junction diffusion capacitance. What is diffusion capacitance? Diffusion capacitance you have studied in the PN junction. I have told you diffusion capacitance between junction, okay, between two region of the device P or N, that is tau I upon eta Vt, right? Tau I upon eta Vt. But for the germanium, eta is 1, so you can write tau I upon Vt. What is the meaning of I? In the BJT, this I is collector current. What is the meaning of tau? Tau means lifetime of minority carrier in the base. Okay, because in the BJT, base is lightly doped, ammeter is heavily doped. So it is a, suppose if it is a PNP transistor, P-type ammeter is heavily doped, N-type base is lightly doped. So lifetime of holes in the base region is important. Or we can say for the BJT, you can write this equation as tau B, lifetime of minority carrier in the base, into collector current IC upon thermal voltage. So this we have to find out. IC is given in the question, Vt is also given in the question, but tau B is not given. What is the way to calculate tau B? Tau B hota hai, tau B is base width squared WB square upon 2 dB. This is the basic formula. So tau B is WB square upon 2 dB. WB is 1 micrometer, that is 1 into 10 power minus 4, its square, upon 2 times of diffusion constant of minority carrier in the base. It is given 45. So it is 45. So it is 10 to the power of minus 8 upon 90. This is tau B. So just put all the values over here. So this is CE is equals to tau B is 10 to power minus 8 upon 90. IC is how much? Collector current 2 milliampere, 2 into 10 power minus 3. Divided by thermal voltage is how much? 25 millivolt. That is 25 into 10 power minus 3. 10 power minus 3, 10 power minus 3 cancel. This is 2 upon 90 into 25 into 10 power minus 8. So it is 2 upon 90 into 25 into 10 to the power of minus 8. So it is 8.88 and 8, 10 to the power of minus 12 farad. Capacitor unit is farad. So we have to find out in the picofarad. Picofarad means 10 to the power minus 12 is pico. So it is 8.88 picofarad. Okay, it is picofarad. So correct to 2 decimal place. So it is 8.88 or 8.89 picofarad. This is the answer for this question. Okay. Now let's solve this question. This is again very simple, designed by me. Okay. Consider two identically doped, identical dimension BJT biased or operated according to the connection as shown in figure. So both the BJTs are identical, only biasing is difference. In this case, base is left open, collector and ammeter are connected with some voltage V. Here, ammeter is left open, collector and base are connected by a voltage of V. Collector base junction is reverse wise by this voltage, and collector to ammeter voltage is like this. Okay, this is VC. Okay. If current gain of BJT beta is 50 and current I2 flowing in BJT2 is 20 nanoampere. So in this BJT second, this I2 is 20 nanoampere. So what is given to you? This I2 is given. Beta is given for both the BJTs. Then select the correct statement. MSQ question I am drawing. Okay, so these are the options given. So this is the drawing for solution purpose. So option is current I1 flowing in the BJT 1 is 1.02 microampere. So the question is, first of all, I2 is given to you 20 nanoampere. So here this I2 is given 20 nanoampere. What is the meaning of this I2? This I2 is flowing in collector base junction from N to P direction like this, like this. It is nothing but ICB naught. When ammeter is left open, what is the current in collector base junction? That is known as ICB naught. And this current I1 is nothing but when base is left open, so this current is nothing but it is known as ICE naught. So can you calculate this ICE naught? If this ICB naught is 20 nanoampere, ICE naught is 1 plus beta times of ICB naught, my dear friend. 1 plus beta. Beta is given how much? 50. Beta is 50, then it will be 51 times of ICB naught. And that is nothing but 51 into 20 is how much? 51 into 20. 1020. And this is nanoampere. So nanoampere. Can you write in the micro? Because BJT 1 is this. A current is given in micro. So convert it in the micro. So it is nano and it is 1.020 microampere. So now let's check first statement. Current I1 flowing in BJT 1 is 1.02 microampere. 1.02 microampere. Yes, it is correct. Current I1 flowing in BJT 1 is approximately 0.39 nanoampere. No, wrong. Next, breakdown voltage of collector base junction of BJT 1 is greater than BJT 2. Now it is about, this is ammeter left open, this is base left open. So we have to think about the breakdown voltage when ammeter left open and base left open. You know very well, BVCEO is equals to BVCBO into 1 upon beta power some 1 by n, some empirical constant. It is not eta. From here we know very well the BVCEO is much less than BVCBO. Meaning is that breakdown voltage when base is left open is small and breakdown voltage when ammeter is left open is more. So in this case base is left open, so BJT 1 will have more breakdown voltage, and BJT 2 when ammeter is left open, this will have less breakdown voltage. So BJT 1 breakdown voltage will be more, its breakdown voltage will be more. Okay, so breakdown voltage of collector base junction of BJT 1 is greater than BJT 2. Yes, it is correct. And for breakdown voltage of collector base junction of BJT 1 is less than BJT 2. No, it is wrong. So A and B are correct. So answer is A and B. A and B. These two are the answer. A and B are correct. And C and D are wrong. Any problem? Okay. Let's see this question. Again designed by me. Question is, which of the following is the correct electric field profile in an NPN transistor? You are having NPN transistor, okay, at equilibrium. So NPN transistor at equilibrium you are having. Which one of the following is the electric field profile? If this PN junction, this complete BJT is abrupt doping profile it is having. Considering that abrupt doping profile in each region with ammeter doping is greater than base doping compared to collector doping. Junction J is ammeter junction, JC means collector junction. And these are the profiles you are having. Which one of the following will be correct for NPN transistor? Okay, let's draw it. Okay, so let's draw it and just solve. Suppose you are having, this is your NPN transistor. This is your NPN transistor. This is ammeter junction and this is your base junction. This is ammeter doping is Ne, base doping Nb, collector doping is Nc, ammeter base collector, and it is given in the question NPN transistor. This is N type, this is P type, and this is N type. At equilibrium you will be having some depletion layer. Obviously ammeter is heavily doped, so depletion layer thickness will be less. Base is lightly doped compared to ammeter, so depletion layer thickness will be more compared to that. Okay, again here collector is lightest dope compared to base, so base will have a small thickness of the depletion layer compared to collector. Okay, obviously this is N side, so here you will be having positive ions, here in the depletion region you are having negative ions. This is PN junction, again N side positive ions, P side negative, and this is neutral P region, this is neutral N region, and this is neutral N region. Now you have to design the electric field profile. Okay, we can design, you can design charge density as well, electric field and potential, everything. Okay, so I am interested over here only in the electric field. What is the internal electric field direction over here? Like this. What is the direction of internal electric field over here? From positive charge to negative charge. Okay, here electric field is going in plus X, and since diode is abrupt doping, it is having, diode is having abrupt doping. Abrupt doping means constant charge density, then electric field is linear. Okay, so electric field plot will be outside depletion region, 0 electric field first of all. This is neutral region, electric field is 0. This is neutral region, electric field is 0. Now inside depletion region, electric field here will be some linear kind of electric field, but the point is whether you will draw downside or upside. Electric field is going in plus X. If it is going in the plus X, just draw in the upward direction like this. Okay, now here electric field is going in minus X direction. Linear electric field you have to draw because charge density is constant, abrupt doping we are having. So downside you have to draw like this. So this will be the plot of electric field. And remember, since this PN junction is heavily doped compared to this, so this height will be more and this height will be less. Meaning is that this peak value of electric field will be higher and this peak value of electric field will be lower. Okay, so this will be the plot. Okay, so the plot is here both are in the same shape. Here they are having alternate. This is both are downside. Okay, so first one is upside, second one is downside. Option C is correct. So C is the answer for this question. Okay, so C is the answer. So these are the 20 questions for today. Okay, now important thing is this is our Telegram group, my dear friend, official Telegram group where you can connect with me and you can have all the idea about upcoming sessions as well. And the important thing that again I want to announce is today at 7 p.m. in the evening, we are going to have a Maha Abhyas where we have planned for the 20 questions. And I told you these 20 questions will be of difficult level definitely. And you will be having some lengthy calculation like generation, recombination process related, continuity equation related questions, 3-4 questions I am going to discuss. Okay. But before that, I have to complete the Maha revision that got stopped yesterday suddenly because of the internet failure. So that's why we will cover our remaining portion of Maha revision, MOS capture, MOSFET and BJT first. And then it will be taking some time definitely. And then we will be going for the solution of the questions in that session itself. So that's why out of 20, I will solve some less question like 10, 12. How much time is remaining for that according to that, and then remaining question you must try, and definitely I am leaving the answer for that particular question over there so that you will be able to solve question and can verify your answer also. Okay, and even though after attempting this 7 p.m. Session, if you find any difficulty, you can connect with me by this Telegram link. Okay, so see you in the evening at 7 p.m. where we will discuss Maha revision and then very important questions, okay, tricky and difficult level questions we will be discussing today. These questions are conceptual, these are important, okay. Thank you very much. See you in the evening. Till then, Jai Hind, Jai Bharat. Bye-bye.